Okay, so this is the 16.4 notes in the ANOVA section for statistics honors. So in the previous section, we talked about that when you had an ANOVA, let's say you had 4 populations, just as an example. Right? The null is always a statement of equality, so we're basically saying the means are the same across all 4 populations, and the alternative is that not all means are the same. Equal. Okay, so the key was if we rejected H naught, that meant that not all means are equal, but we didn't necessarily know which means weren't equal. So for example, maybe, mu1 and mu2 are equal, but mu3 and mu4 are not. So it's kind of an issue there because maybe you'd like to know what means are actually causing the test to blow up and end up rejecting H naught. So that's what the focus of the section is. We actually call a very funny name test called the Tukey multi-week comparison method. It's like turkey without an R. We use that in order to, it's actually a group of confidence intervals that compare every pair of means from each population in order to determine which ones are actually blowing the problem up, creating a significance results, and rejecting H naught. Okay, let's talk about some things to know about the Tukey method. First one, I'm going to read. It says, while you're used to individual confidence levels for each class, the Tukey method utilizes a family confidence level. So what does this family confidence level do? It basically covers all the confidence levels you're going to be calculating. So instead of doing an individual one for each, they basically do a family confidence level that encompasses all of them. Next, the Tukey method is based on what's called the Q distribution, or formally the studentized range distribution. This is also a right-skewed curve, just like F, but it has 2 parameters. It's called K for kappa and V for nu. Okay, so kappa and nu. These will be defined in a second, but basically there is a table, so real quick. So there is a Q table right here. So you can see there's a Q sub 0.01 and there's a Q sub 0.05 table that we use, but that is it. So we only deal with alphas that are 0.01 and 0.05. Those are the most common ones when doing this for ANOVA problems, which means we're going to be doing the same thing for Tukey. So you can see in these tables we have kappa and nu across the top and across down the column. So those are the values we're going to use in order to find the important values in the chart for Q. So just to be clear on that when we're going through it. Okay, so here's the Tukey multi-comparison method. Some of it's a little bit odd to read, but I'm going to do my best to sort of explain. So the assumptions are the same for ANOVA and Tukey. I usually don't. Usually you do an ANOVA, you make sure the assumptions are okay. You don't check them again to do Tukey. So in this scenario, that is we just sort of let that go because they've already been checked already. You have to decide on a family confidence level, which is always going to be 1 minus alpha. So why do we have to do 1 minus alpha and a confidence level? Because these are confidence intervals. So in ANOVA, you're going to be giving a significance level, alpha, to do the test. So when you're done with the test, if you determine that you have rejected H naught, that means you want to figure out why. So just to be clear, you only run a Tukey method if you reject H naught. That's a big, big statement right there, so make sure you keep note of that somewhere. You only do a Tukey method if you reject H naught. So if you do reject H naught, you're going to use confidence levels. The alpha was what's given to you, so you do the 1 minus alpha to find the confidence level for your confidence intervals. Okay, you're also going to have to find the value of Q sub alpha with kappa and nu. That's going to be actually in the formula I'm going to show you in a second. Literally a second, because here we are. So the formula for each interval that you're going to create is right here. So it actually looks kind of similar to some of the things that we've done before, because we have the sum of the 1 over n's over here in a square root, but basically this is what you're going to do. You're going to take the q sub alpha that you calculated here in the table, you're going to divide by root 2 every time. So that's not a variable, that is literally divide by root 2. Then you're going to multiply by s times the square root of the 1 over n, the sum of the 1 over n's. Now s is actually equivalent to the square root of MSE. In the ANOVA calculation, you have computed this already, so this is not a big deal. But one thing to take note of here, it says do so, in other words, calculate the interval for all possible pairs of means. Okay, so that means what we're going to have to do is we're going to have to go to our null, and we're going to have to go, well, how many are there? One, that's another pair, that's another pair. Well, you can do that if you want, but we also have combinations to figure that out. So we'll talk about that in a second. So combinations will tell you how many intervals you actually have to calculate. Okay, so step 4, it says, declare two population means different if the confidence interval for their difference does not contain 0. So again, we've done this before. If it doesn't contain 0 in the actual interval itself, that means there is a difference actually going on, because remember, 0 means no difference. So just like we've done before, that's going to be sort of our setup, and then there's going to be a summary and interpretation thereafter. Okay, we're going to do one example of this, and logically we're going to go back to the energy consumption problem. So in the energy consumption problem, remember we had 4 regions, right? And we had data for each one. We already ran an ANOVA, a complete ANOVA, and we already determined that we rejected the null hypothesis, that the energy consumption is the same for all 4 regions. But again, we don't know which ones are the problems. Which pair is causing this test to create significance results? I call it blow up, meaning reject H naught. We don't know that. So that's what we're actually now going to find. Is it northeast and midwest causes it to blow up? Is it midwest and west causes it to blow up? We don't know. But that's what we're going to actually find to do. So let's go through the process. It says, ideally we start by identifying the family confidence level. How do we do that? We do 1 minus alpha. So alpha in the original energy consumption problem was 0.05. So we're going to do 1 minus 0.05, 1 minus alpha, to determine that our family confidence level is 95%. So we're going to be running all of our tests at a 95% confidence level for a scenario. What else? Well, we move on to the Q distribution for K and nu. So it's going to be basically kappa and nu. Now, if we return back to this setup right here, I know we got a lot of drawing on here. Let me get rid of it all. So the formula for kappa and nu are right here. So they're a little bit different than ANOVA. So remember, the first variable was always k minus 1. This was just going to be k. So our kappa is going to be our k in this scenario. Remember, k is the number of population, so that is 4. Our nu is going to be n minus k. Well, remember, n represented the sum of all of the possible samples. I believe that was 20 for our ANOVA problem, and we're going to subtract 4, which is going to give us 16. So what are we looking up? We need to find the value of q sub alpha for our problem. So we need to find q sub alpha, which is 0.05, at 4 and 16 for kappa and nu. So I just did a summary, then we'll go to the table in a second. So kappa and nu, we need 4 and 16. So if we go down and over, we're going to go to 4.05 for our value of q sub 0.05. Why do we need that? Because if you look back at the formula, we need q sub alpha in the formula. So we're going to have 4.05 divided by root 2 in every single interval problem that we do for the sake of this. And just to be clear, if we go to the q table, right, if we go to the q, so the q 0.05 right here, we have kappa and nu. Again, what are the parameters? It was 4 and it was 16, right? So if we had the full table, we would go and we would find 4.05 as our value for Q sub alpha, 4.05. Okay, so how are these intervals actually calculated? All right, I'm going to read this. It says, now we must compute the confidence interval for every single pair of mean consumptions in this study. Remember that we can determine the total number of pairs utilizing combinations. Since there are 4 regions and we want to take 2 at a time, we do 4C2. If you put that in the calculator, you're going to get 6 pairs of regions, which means we need 6 confidence intervals in order to move on. Now, we're not going to calculate all of them. We're going to do 2 of them, and then I'm going to show you the rest of them for interpretation purposes. But it's valuable to calculate 2 of them to make sure that you understand what you're doing. So I brought back the formula here for you. Remember that we already did these values, 4.05 over root 2. So we just have to find S. Well, S is equal to the square root of MSE. So if you recall, you might not. I don't know. So if we go back and look at, let's see if we can find it. So the MSE for the consumption problem, MSE, there it is. So the MSE for the energy consumption problem was 5.581. So if we go back and we do S is equal to the square root of 5.581, and we put that in our formula right here. Okay, that's where it's going to go. So what I'm going to do is I'm going to go through the calculations. I also brought back a summary of all of our important information. So basically, J is not that important. That just means this is the first, second, third, and fourth population. But I brought back the means for each of them, and I brought back the sample sizes for each of them. So again, we're talking about this data right here, right? So the sample size is 5, 6, 4, 5, and then the means, I think I listed them a long time ago at the bottom of the chart. Those are actually brought back as well in order to do the calculation. So let's do them. So remember, this is the formula right here. I'm going to leave it at the top so we can use it as a guide, right? So we're going to do the first mean minus the second mean. So let's say we start with Northeast versus Midwest. So it's going to be this one and this one. So we're going to do our first mean, which is 11, minus our second mean, which is 12.5. We're going to do plus or minus. Remember, we're doing 4.05, which is our Q sub alpha over root 2. And we're multiplying by the square root of 5.581. So I figured I could have found that value here and put it in, but why not just keep the radical? There's no harm in that. So that's going to be times the square root of 1 over the first sample size, which is 5, plus 1 over the second sample size, which is 6. So if you do this entire calculation, you're going to get negative 1.5 plus or minus. This entire second piece is going to be 4.10. So if we do the interval, we're going to get negative 5.60 to 2.60. All right, so that is our first confidence interval for our Tukey multi-comparison that's taking Northeast versus Midwest. Now, just before we move on, notice what value is not in here. 0 not... Oh, 0 is. Oh, 0 is in there. 0 is in interval. Right? I am blind. Yeah, 0 is in the interval. So basically, if 0 is in the interval, that means there's no difference between Northeast and Midwest. So if there's no difference between them, that means those are the two that didn't make this sucker blow up and create a rejection. They are comparable energy consumptions. So that's the first thing here. So let's try another calculation. So let's say we did Northeast versus South, right? So now these two. That's our second of our 6. So let's do the same thing. So this time, the means are 11.0 and 7.5. So we're going to do 11.0 minus 7.5. And then the right side is all almost entirely identical until the sample size is 4.5, root 2, 5.581, right? But then you have to be careful with the sample size. So this is obviously still 5, but the other one is 1 over 4. If we do the calculations, we're going to get 3.5 on this side, and we're going to get 4.54 on this side. So we go over here, we do the math, we get negative 1.04 and 8.04 for our interval. Again, though, 0 is in interval. If it's in the interval, that means there is no difference between the values. So now we know that comparing northeast and south didn't blow this thing up. So clearly, those would not be the problem. There's no significant difference between those two means. Okay, so we could sit here and do all four others. I'm confident that you guys can easily calculate the rest of these using this table. So what I did was, if you note, look at my intervals here. So this one and this one are here and here. So I created this little table that basically compared, if you can see, northeast to midwest is this interval here. Then if we do, let me get rid of this so we can color code. So let's say now we decide to do northeast versus south. So northeast versus south, that's going to be this one, which is right here. So it's actually a very funky way to determine, it's like a cross way to determine. So all four other intervals are then calculated for the sake of our problem, and the 6 results, remember, 6 intervals, are in this table. Okay, so I'm going to read the interpretation. It says right here, if you recall from the work you did with t intervals, we rejected the null of equal means whenever 0 was absent from the interval. Observe the chart of intervals above. It appears that midwest and south, and then midwest and west, which are these two, have consumptions that did not have 0 in their respective intervals. Therefore, we can declare their mean energy consumption different. So what was the issue? So Midwest compared to South and Midwest compared to West were the two sets of means that actually caused this to be rejected. So it's actually, Tukey is pretty awesome, because what it does, and ANOVA is a very common statistical method in research, it basically breaks things down for you. So you go, okay, well, we did this big test, but now we know what the culprits are. That's the best way to put it. The culprit is taking Midwest versus South and Midwest versus West. That is when this whole thing's wet. And to be clear, we actually, since Midwest comes first here, we did Midwest minus South, Midwest minus West to get these values. Note that they're positive. So it also tells us that the Midwest is significantly higher than the other two. Now let's just verify that here. Can you see that Midwest is 12.5 and we're comparing it to South and West? So you can see that they are, just the means are significantly higher. So it makes sense that that is the case in this scenario based on these values. So in the end, the Tukey comparison method is basically a group of intervals for every pair of means from our original test. So remember, if we go back here and we look at our original test, where did I put it? I'm going to write it. So mu1 equals mu2 equals mu3 equals mu4, right? So it's taking every pair and you're finding which ones are blowing up the process, creating significant results by rejecting them at H0, which ones are different. So in this scenario, you actually found that mu2 compared to mu3 and mu2 compared to mu4, mu2 compared to 3 and 4, were the actual problems that resulted in the results not to be significant in the original ANOVA test. So that's what Tukey's for. Now note, remember this semester is a little bit different. Normally you use Tukey only in the semester project and I don't test on it. Right now, I don't know if that's the case or not, but you are going to have your notes in front of you for the remote testing. So just note that right now you want to know this just as much as the other thing. You are going to do all of this in the lab.